So, yeah, they spend most of the paper trying to prove these results for the conversions. So first of all, they prove that this series, call it what? Say double star. This series is double star. So the series double star is an asymptotic expansion in the following sense. In the following sense, if you have the nth partial sum, so Sn is just, identity plus summation k equals 1 up to m minus 1 to this in parentheses. This, I will call this to be the AK, okay? The kth term. Okay? Maybe just not to confuse you guys with too many things, I will write here for the last time. So this is integral tau 1 tau k minus 1 f tau 1 f tau k. The result is a vector field g tau 1. And now on, I will call this to be the kth term. So it's this is the m partial sum. Okay, we truncate the series after a while because we cannot go to infinity. So we're gonna make sure what happens in this case. So you have the following result, that we have the full series exponential of 0t f tau d tau. This guy can act on any C infinity function versus the partial sum acting on the same C infinity function. This is in the order of t to the m as t goes to 0. So for small enough time, the difference is small. And if you consider your differential equation for perturbation, epsilon that we use in average, you can have epsilon here or not, doesn't matter, but there is epsilon outside, then the difference between this solution, again exponential, f tau d tau, acting on h minus Sm, here we have epsilon, right? So here we have epsilon multiplying f, acting on h, is order epsilon to the m, okay? As epsilon goes to 0. These two results are for any h in C infinity, for any small function, for any h in C infinity. We didn't say anything about the convergence of the series itself because it does not always converge. It converges only wherever the vector field itself converges, the dynamics. So the double star converges on any normed space L that is subset of C infinity, where your vector field is bounded. So, we have a norm of f as a vector field acting on C infinity is bounded. You know the norm of an operator. I'm just reminding you, this is the norm of any operator. The sup or the max, f acting on any h, right? And you take this guy, h L, and h is norm less than or equal to 1. Okay? This norm of the operator f for the vector field is less than infinity, is bounded. Okay? So if you have any space of functions where this guy is bounded, then the series converges, which makes sense because you keep adding this guy. If it's not bounded, things will blow up. And we have a bound for your series. So the exponential, this is your series, right? acting on h, the norm of this is actually this, then or equal the exponential of 0 to t, the norm of f, we just defined d tau, times the norm of h. So this shows that if this guy is bounded, then this guy is bounded. So, yes?
So is this condition equivalent to the existence condition for the solution for the differential equation?
I don't think so.
So
It's more.
So this is as
So actually, this is trivially satisfied if you have a finite dimensional space. That's it. So if we're talking about Rn, so this would be trivially satisfied. You will have this guy's bounded, and that's it. So we have the series convergence. So I'm trying to say is that this is just a technical subtlety. It's not a big thing. But just be aware that this series does not converge for any function. Any smooth function, you just come up with it in a pedantic way. It may not converge. It just converges wherever this guy, your meet, converges. The vector field itself. Most of the cases, things are nice and converge. So far we did not do anything, but okay, it's some good math, that's okay. But indeed, it's a series solution, okay, for a differential equation, which, we hear about from very, very long time. Series solution for differential, whenever mathematicians, or particularly engineers or, physicists, they start with a differential equation, they assume a series solution, right? It's very famous in engineering, in beam theory or what, plate theory, whenever we start, or even in the, in aerodynamics, fundamental integral differential equation, we assume a series solution, okay. So this is very well known. So this is nothing but a series solution. It's not fancy thing, okay? But the way it's written can be beneficial. Like, let's look at the form, because now we have a series solution written beautifully in terms of linear derivatives, so we can answer the following question. So given this differential equation, so given x dot is f of t and x, okay. So now then you have time varying differential equation, non-autonomous. What is the autonomous vector field V whose flow for unit time matches the flow along the time varying vector field for time t? In other words, can I replace my time varying differential equation with a time invariant differential equation? Okay? What is the equivalent time invariant differential equation? Any question about the question? Do you get the idea? So, in our language, the question can be posed super simply. We are looking for V such that the flow along f for time t is equivalent to the flow along V for unit time, right? Look at how simple the mathematics make it. Right? We're looking for this. Well, we have an exponential representation for this guy. Let's write it term by term. So we have, this is identity plus summation. Let's write the first two terms. So this is 0t f tau d tau plus 0t 0 tau 1 f tau 1 acting on f tau 2, which involves differentiation d tau 2 d tau 1 blah blah, equals the flow along V for unit time. V is time invariant. So either you use Grobner expansion or use this expansion as well with V instead of F, and you know that V is constant, so you can take it outside. So the double integral gives you t squared over 2, and this is t. The next integral is t cubed over 6, and so on and so forth. So this is indeed, again, identity plus the time, which is 1 here for time, times v divided by 1, it doesn't matter, so plus, again 1, your time is 1 squared divided by 2, v squared, which is v acting on v, and so, right? Any question about that? So just one note here, just one note. Obviously v, from the definition, v is time invariant. Okay, we understand. But look at this here. Yes, we're looking for a time invariant v, but it will depend on t. It will be parameterized by t. So, in the following sense, I want a differential equation autonomous, time invariant, whose solution after 10 seconds matches my solutions. Whose solution matches my solution after 10 seconds. Whose solution for 1 second matches my solution for 10 seconds. Yeah? Well, okay, we can do this and give you a differential equation. But if you want to do something for 5 seconds, I want a differential equation whose solution for 1 second matches mine for 5 seconds. Well, it will be a different differential equation, right? So this is parameterized by t. V is autonomous, yes, but parameterized by t. So we will denote it by Vt. Okay? So this is Vt, Vt, Vt. So from this equivalence we can get Vt. From this equivalence we can write Vt, and it will be a series thing. So this is summation k equals 1 to infinity, our usual integral, 0 tau 1, 0 tau k minus 1. I want to remind you of something. This is Vt acting on Vt, right? I'm reminding you of the following. Remember, what's the Lie bracket between x and y? It's just x acting on y minus y acting on x. This action is the same action as we defining here, actually. Okay. So when you equate these two series and take this into account, you can write here everything in terms of Lie brackets. So this would be actually some functions, just Lie brackets of these f's, f tau 1, f tau k. So take Lie brackets of your f's at different time and do this iterated integral. You get the time invariant differential equation, the equivalent time invariant differential equation. G's is just Lie brackets. What do you mean by Lie brackets? Well, you need to do it term by term to discover these G's, unfortunately. So G1 of F1, for example, of tau 1, is just, of course, the F. And G2 of F tau 1, F tau 2 is 1/2 Lie bracket F tau 2 and F tau 1. G3 of F1, F2, F3 is just 1/6, 3 with 2 and 1, and 3, 2, the result with 1. So you can have the first few, you can read the first few either, so all these G's are just Lie brackets between vector fields, and you can read them from the paper by Agrachev and Gamkrelidze. (1978), or from Vela's thesis, 2003. So, for example, this is Vela dissertation. Here are the functions. Okay, you just call them V's. So this is zeta 1. The add is just the Lie bracket, right? And here's the thing, this is just an illustration for it. So, okay, so you can write them. This is page what? 28? Page 22 in Vela's dissertation. Okay? So these G's functions, just Lie brackets. It's nice, but it's really not useful at all. You're saying that if you want to change the time, I go and get a new differential equation. This is not really useful unless you have a magic time that you want to track, right? If there is a magic time you want your differential equation, okay. Otherwise, this is not useful at all, right? Why are you guys doing it? So in their paper, there was not a magic time. And we're done with the chronological calculus. One other benefits of the chronological calculus is what we had last time, the variation of constants formula, so other things. Yeah, sorry about that. It's last lecture anyway. Okay. So other benefits from chronological calculus is the variation of constants formula that we had last time, very useful tool. The series for the pullback of this guy, if you remember. The series, which is f plus, the series of iterated integrals we had last time. So this all come from the chronological calculus. The paper is ended. That's great. We're done. Nothing, nothing it has very interesting tools, very useful tools, particularly the variation of constants formula. I like it so much, and I'll give you an example in the homework so that you can appreciate it. But let's see how Sarachev and Vela use these tools to enhance averaging. So far, we mentioned nothing about averaging, right? So let's take a deep breath now and try to look at averaging. We want to enhance averaging. Any questions so far? So we have x dot equals f of t and x, and f is periodic in t. This is our one differential equation, a nonlinear time varying in general, it's time periodic, right? And we know we have two approaches. We have Floquet, and the very first step of Floquet is just, I will not be that meticulous, it's equilibrium and linearization. Why? To put it in the canonical form of Floquet, z dot equals a of t times z, this is t periodic. Floquet indeed applied to this linear time periodic. This is a linear time periodic version. I will call this one linear time periodic version. How we apply Floquet? When we just simulate this guy for n independent initial conditions, preferably the identity. Please get your 5t. This is our monodromy matrix. Check the eigenvalues. Alternatively, you can use the following transformation, that z is p of t times y of t, and now you have the y dynamic